What's up, my fabulous fam? It's your girl Naia, back at it again with another reaction that's about to blow your mind. Today, we're diving into the wild world of Minecraft with a video titled I Made an AI with Just Redstone by the one and only mattbatwings. Ow, I don't know about you, but the thought of an AI built with just blocks and wires has me shook. Like, how does that even work? Get ready for some epic creativity, maybe a few laugh out loud moments, and definitely some surprises along the way if you're as curious as I am. Make sure to stick around, and hey, if you're loving the vibes, hit that subscribe button and give me a thumbs up. Let's jump right into this madness and see what kind of genius or chaos mattbatwings has cooked up. Let's go.
I made a fully working neural network in Minecraft. You can draw a number on this drawing pad, and it'll tell you what you drew. This is the story of how I made this project, from researching to running simulations to building all the redstone.
That's wild. Building a neural network in Minecraft is next level creativity. The amount of redstone work must have taken forever. Can't wait to see how it all comes together.
I hope you enjoy. This story starts a few years ago, when I was taking a machine learning class at university. On the first day of class, the professor showed us some basic neural networks and how they could learn things like humans do. And as someone who did Redstone, I wondered if it was possible to make a neural network in Minecraft. I mean, how cool would it be to build something in your world and watch it learn? Especially if it could learn something complex, like image classification. So later that day, I went on YouTube to see if anyone else had done it before. To my surprise, almost no one had. At least, not with just Redstone. There were a few people that did it with command blocks, but I could only find one person who built a Redstone-only neural network, Yannick Kilcher. After watching the video, I was really impressed, but at the same time, I was a little bit disappointed. Not in Yannick, he did a great job, but just in the size of the network. If neural networks are already this big and complex for just a few neurons...
Whoa, just look at that setup. If this is what a few neurons look like, I can't even imagine the scale of a full neural network. It's like a whole city of redstone.
A few neurons, then making something like an image classifier seemed completely out of reach. So I scrapped the idea and I just made other kinds of projects for my channel. But then, in the summer of 2022, this video popped up on my recommended, and I immediately clicked on it. A team of people made a convolutional neural network, and they used it to recognize handwritten digits. You could draw a number on the screen, and the network would tell you which number it thinks it is, along with a confidence value. Suddenly, my opinion on neural networks completely changed. Clearly, it was not only possible to do cool stuff with them, but also keep them in a relatively small footprint. Now, for better or for worse, I'm a very competitive person, so I quickly became fixated on making an even better neural network than this. I wanted to make a handwritten digit recognizer that was faster and had better accuracy. Whether this was possible or not, it didn't matter. My competitiveness meant that I was about to spend a lot of time trying to make this happen. There are lots of different kinds of neural networks, so first I had to decide which type of network to use. After looking at some handwritten digit networks online, it seemed like most of them either used a multi-layer perceptron or...
That's a classic choice. Multi-layer perceptrons are like the OG of neural networks. It's cool to see how they're still relevant in projects today.
Perceptron, or a convolutional neural network, which is what the team used. Both MLPs and CNNs can get pretty high accuracy on handwritten digits, so I actually decided to go with an MLP because it seemed easier. This was a bold choice, considering the team didn't do this, and they clearly knew what they were doing, but I just had a gut feeling that an MLP would be better suited for Redstone. Now, if you haven't seen MLPs before, 3Blue1Brown has an absolutely incredible video on them, and it's on handwritten digit recognition too, so I highly recommend watching it, but I'll give a shorter explanation here too. An MLP is a function, with input and output. In my case, the input is all the pixel values of the handwritten digit, 0 being black, all the way to 1 being white, and the output is 10 numbers, representing the confidence the network has for each digit. If you put in the pixel values of this image, for example, a smart MLP would output a high confidence for 3 and a low confidence for everything else. But for simplicity, consider an MLP with just 2 inputs and 2 outputs. Inside the MLP, there are neurons and connections between the neurons.
This is a classic neural network diagram. It's fascinating to see how these connections work together. The way neurons interact is like a brain in action, so cool.
Every connection has a weight, which is a number that represents the strength of that connection, and every neuron has a bias, which represents how likely or unlikely it is to fire. When you input something to the network, like 1 and 2 for example, they get sent out by the connections and multiplied by the weights. Then, for each neuron in the next layer, all the numbers that arrived get added up, and the bias of each neuron gets added as well. Then these neurons send their values to the next layer, and the process repeats itself. Every column of neurons is called a layer, and these layers have special names. The first one is the input layer, the last one is the output layer, and anything in between is a hidden layer. In general, you can have as many hidden layers as you want, and within any layer, you can have as many neurons as you want. So there's a huge variety for what an MLP can look like.
It's Alan.
Seriously? The Alan?
Wait.
In the case of handwritten digit recognition, the input layer has as many neurons as there are pixels in the image, and the output layer has 10 neurons. Now, as I've described the network so far, it's just doing a bunch of multiplications and additions.
This is where the magic happens. It's wild to think that all those multiplications and additions lead to recognizing digits. It's like a math party in there.
Additions. That's great, but it also means that if you're good at linear algebra, you can reduce the entire network down to an equivalent network with just an input and output layer. So there's actually one more thing an MLP does. After a hidden layer outputs its numbers, an activation function is applied before passing it along. One of the simplest activation functions is called rectified linear unit, or ReLU. ReLU just says if it's negative, set it to 0. Otherwise, don't change it. So let's apply a ReLU to the output of the hidden layer, and as you can see, the negatives become 0. Then they get passed along. Another way to think about activation functions is that they're kind of analogous to a real neuron. The output is 0 until you hit a certain threshold, which makes the neuron fire. So that's how an MLP is executed, but how does it actually learn to recognize digits? Well, it has to be trained. In other words, it has to learn the weights and biases that give the best accuracy. This is typically done by showing the network tons of examples and using an algorithm called backpropagation to continuously update the weights and biases.
Backpropagation is where the real learning happens. It's like the network's way of saying, oops, I messed up, and then fixing itself. Super cool how it fine-tunes everything.
And hopefully, after showing it lots and lots of examples, you can then show it a brand new digit and it'll make a prediction based on what it's learned. Now that I had a better grasp on MLPs, I created a plan for the rest of the project. First, I wanted to simulate and train the entire network in Python. That way, if the Redstone had an issue later, I'd have a reference to compare it to. Then, I wanted to build it in Minecraft and import the weights and biases from the code, so the Redstone would only execute a forward pass through the network. In Python, I started by importing the MNIST dataset, which has thousands of examples of handwritten digits. Every example is 28 by 28 pixels, and it's labeled with the correct number. Then I used a package called Keras to build the network. I made the input layer 784 neurons, one for every pixel in the image. And then I didn't know how many hidden layers I was going to need, so I started off with just one hidden layer of 32 neurons and a ReLU activation. And then I made an output layer of 10 neurons. Once that was done, I used this code to train the network. And after testing it, it got a really high accuracy of 96%.
That's impressive. A 96 accuracy is no joke. It's awesome to see how well the network learned from the data. This is shaping up to be a solid project.
Of 96%. Then I continuously reduced the number of neurons in the hidden layer, seeing how it affects the accuracy. And I ended up finding a sweet spot at about 10 neurons, which still gave pretty good accuracy, 92%. And now I had an actual structure for my network. 784 input neurons, 10 hidden layer neurons, a ReLU, and 10 output neurons. But this is when I ran into my first big problem. The images in the MNIST dataset are grayscale, and there's no easy way to show a grayscale image in Minecraft. I mean, technically there is, but how would the player even draw one anyways? The best you can do is draw an image on redstone lamps, which are only on or off. So using this code, I made all the pixels in the dataset snap to either black or white, depending on which one they're closer to. I retrained the network, and the accuracy was still 92%. However, I found another big problem. The weights and biases are stored internally as floating point numbers, which are really difficult to work with in Minecraft. In fact, almost no one does it. Most people just work with integers.
That makes total sense. Working with integers simplifies things a lot in Minecraft. It's interesting to see how practical limitations shape the way you approach building these networks.
I tried rounding all the weights to the nearest integer, but because of how precise they were, this lost a ton of accuracy. But then, I had a pretty good idea. I decided to multiply the weights by 100 and then round them. This works because the exact value of a weight doesn't really matter. What matters more is how the weights relate to each other. So this strategy allowed me to get more precision, convert them to integers, and keep their relative relationships. I tested the network again, and it still got decent accuracy, 83%. Obviously it's not amazing, but it was still better than my self-imposed competition. With the simulation working, it was time to start building the redstone. I started with the drawing tablet, which would allow the player to draw a number by moving around on a platform. Luckily, I had already built this exact thing before in my redstone paint program. It used tripwires and string to detect where the player was standing and sent that information to the screen. So I ripped it out of the paint build and I modified it to be 28 by 28 pixels. I tested it out and it worked beautifully. When I sped up the game using Carpet Mod, I was able to draw in nearly real time.
That's awesome. Drawing in nearly real time is a game changer. It must feel so satisfying to see your creations come to life that quickly in Minecraft.
I also explored some other options like pressure plates and throwing snowballs at the screen, but it seemed like nothing could beat the elegance of tripwires. The only problem was that the data was hard to access because the XY decoder was right behind the screen. So I duplicated the redstone and kind of mirrored it like this. That way when I drew something, it created two copies, one on the screen and one over here so that I could easily access the data. And with that, the input layer was basically done. These are the 784 ones and zeros that get put into the network.
Consumindo-se e liberta a tua magia.
Equipa de segurança da Bolt, ao teu lado, em cada viagem.
Next, I started working on the hidden layer. Thinking about all 10 neurons at once was really overwhelming, so I started by focusing on just one. Remember, a neuron takes all the numbers from the previous layer, multiplies them by the weights, sums them up, and adds the bias. At first, this sounded like a monumental task. 784 multiplications? That's insane for a redstone build. But then I remembered that this isn't grayscale anymore. The input numbers are just ones and zeros, so the multiplication is trivial. Just keep the weight if it's a 1, or throw out the weight if it's a 0.
That's a clever shortcut. Simplifying the multiplication like that makes the whole process way more manageable. It's all about working smart, not hard.
0. Then just add up the weights you kept, and add the bias. The other cool thing was that the weights and biases only had a range of -5 to 5. That's only 11 numbers, so I decided to represent each weight as a signal strength value with a barrel. So here's the first prototype I made for one neuron in the hidden layer. Every weight in these barrels is being read by a comparator, but if the pixel behind the weight is 0, the comparator gets cancelled. When I press this button, all the weights that aren't cancelled get put onto this main line, and they come out over here in a stream. So if the weights are like this, and every pixel is on, you get all of them. But if only the 4 corners are on, you get this. Then to sum them up, I converted them to binary and fed them into a special binary adder to keep a running total. By the way, I didn't make this adder, and I don't really understand how it works, but it's really good at adding up a ton of numbers. It's called a looping carry save adder, designed by Amino. Instead of a normal adder where you would add 2 numbers and get an output, it just has 1 input, and every 2 ticks...
This setup looks intricate. Using a looping carry save adder is a smart move for handling all those calculations efficiently. It's impressive how you're combining redstone with complex logic.
2 ticks, it adds that input to the total, which is extremely fast. For example, if you input 1, 2, 3, 4, all 2 ticks apart from each other, you get 10 almost immediately. This made it a perfect fit for summing up the weights. If all the pixels are on, you get 18, or with the 4 corners, you get 8. And to add the bias, I plan to just add it to the total at the end. After finishing the prototype, I made the first hidden layer neuron for real. Honestly, this went really well. After I finished it, I put in some test weights, and it seemed to be working. The only problem was that it took a long time to run. 784 additions is no joke, even with a really fast adder. So I split up the work into 4 adders running simultaneously, and that made it way faster. Then, to import the real weights, I used a Python package called mc-schematic. I used this code to extract the weights and generate a schematic of barrels, which I could just paste directly into the world. I also used mc-schematic to put in the first example from the real dataset. Once that was on the screen, I ran the neuron.
This setup looks incredible. Running the neuron with the real dataset must be so satisfying to see in action. The visuals are just as impressive as the tech behind it.
And I got the correct value. Then to make the rest of the neurons, it was pretty easy. I just used World Edit to copy and paste it 9 more times, and I pasted in 9 more sets of weights and biases. Instead of testing anything, I decided to just send it and run all 10 at once, which unfortunately didn't work the first time. The other 9 neurons revealed a bunch of bugs that I didn't even realize I had, but eventually I got the output to look like this, which was exactly correct. The only thing left for the hidden layer was the ReLU. Remember, ReLU just sets negative numbers to 0. To my surprise, this was really simple to do. Every number already had a sign bit, which was 1 for a negative number and 0 for a positive number. So I just wired the sign bit into a tower of comparators that set it to 0. That way, if the number was negative, it got cancelled out. Now that I was confident the hidden layer was working, I moved on to the output layer. Just like before, I started by focusing on just one neuron. Unlike the hidden layer, there are 10 multiplications instead of 784. But these multiplications are not necessarily by 0 or 1.
This is getting intense. The output layer math looks complex but super interesting. It's fascinating to see how each weight plays a role in the final output.
0 or 1, so now I needed to use actual multipliers. I looked in my schematics folder to see if I had any multipliers already, and I found 2 designs, but I actually didn't want to use either of these. They didn't work with negative numbers, and they were really big. So big that they couldn't fit side by side here without making me spread the circuit out. So I designed a new multiplier, which was skinny enough to fit 10 of them side by side. Then once I confirmed that they were actually working, I made them all output to this line, which feeds into another looping adder. And now, I was already ready to test the neuron. I imported the weights and biases from output neuron number 9, and when I ran it, it was right. Suddenly, I could see the light at the end of the tunnel. I duplicated it 9 more times, pasted in the rest of the weights and biases, and just like that, the full network was ready to run for the very first time.
To show me that you haven't forgotten.
At this point, the network was working perfectly.
Wow, this setup is massive. It's incredible how you're translating those confidence values into a readable format. The complexity of this build is mind-blowing.
I considered stopping the project here, but there was still something about it that I really didn't like. I had to read the confidence values as binary numbers. So I wanted to figure out how to make the final output easy for anyone to understand. My first idea for this was to make a circuit that finds the maximum and displays it on a screen. So in this case, it would see that 7 has the maximum confidence, and it would display it here. But then I thought, why not display everything? If I could take these values and display them on some kind of bar chart, that would be really cool. Like when you draw a 3, it would be cool to see the bar for 8 go up a little bit since they're similar shapes. However, there was an annoying problem with the bar chart. It needed to be tall enough to account for the smallest and largest possible confidence values, which meant that most of the time, the bars would be really small. But I really wanted a bar chart, so I went to the internet to see how people solved this problem. One solution is called softmax. Softmax is a function that takes a list of numbers and creates a new list of numbers where they're all between 0 and 1, and they add up to 1. So it basically takes the values.
Softmax is a game changer. It's awesome how it normalizes the values, making them easier to interpret. This will definitely enhance the output display.
The values and converts them to probabilities. This was tempting to make in Redstone, but when I saw that there's exponentiation in the formula, I got scared and started looking for another solution. Then I found this formula, which is similar to softmax, but doesn't involve any crazy operations. It basically squishes the list down to a specified range, like 0 to 1 for example. So I thought, why not make that range 0 to 15 and floor it? That way it converts the list to signal strengths. And so this is the formula I decided to build. Ironically, implementing this formula took up more space than the entire network so far. I used a chain of comparisons to find the min and max value, I used shifting and subtraction to multiply by 15, and I used a bunch of dividers to perform that final division. This was obviously a ton of work, but it was worth it. Now the confidence values were just the signal strengths of these 10 redstone dusts. So finally, I made the bar chart. Every bar was 15 lamps high, which allowed me to show all the signal strengths in a really nice way. Overall, I could not be happier with the final build.
This final build looks incredible. The amount of detail and effort you put into it really shines through. It's awesome to see everything come together so well.
Final build. With 83% accuracy and a real-time speed of just 2 minutes, this thing is a beast. If you'd like to try it yourself, there's a world download in the description. I'll see you in the showcase. neural networks can feel really overwhelming.
This is a great visual. It really shows how complex neural networks can be, but seeing it in Minecraft makes it so much more engaging. It's awesome to see the project come to life like this.
Overwhelming as it did for subscription. You'll also get 20% off an annual premium subscription.
That's a solid offer. It's great to see resources that can help people dive deeper into learning about AI and neural networks. Definitely a win-win. Alright, fam. Wow, what a wild ride that was with mattbatwings and his epic journey of building an AI with just redstone in Minecraft. From the insane neural network setup to that jaw-dropping 96 accuracy, I was living for every second of it. It's mind-blowing to think all that math craziness is happening in a game made of blocks. Honestly, seeing the way he made complex concepts like backpropagation and softmax come to life visually in Minecraft, that's just chef's kiss. It's not just gaming, it's a whole new level of creativity and tech magic going down. And let's not forget how satisfying it must be to watch those calculations play out in real time. Turning all that brainy complexity into something you can see now, that's what I call next-level gaming. So, if you enjoyed this epic reaction as much as I did, smash that like button and hit subscribe for more outrageous content like this. Keep that energy flowing because we're just getting started. Thanks for vibing with me today. I can't wait to catch you in the next one. Stay fabulous, fam.